It's important that you have these 4 steps written down before we attempt any limiting excess problems. In this video, I'm going to teach you how to do limiting and excess reactant problems and calculate the unused reactant as well as one of the masses of the product. Very common in chemistry or higher level chemistry, college level chemistry, that you'll have to do these problems. Have a calculator and a periodic table ready before we get started. Next, I'm going to show you a blank setup that works for all of these problems. What makes a problem be a limiting and excess problem is that you start with a mass of both reactants, whether they're an element or a compound. So you're given a mass for both of these, and only one of these will be consumed typically completely to produce your products. So what you're going to do is start with those masses, and because these are mole amounts, we need the mole amount of each of those reactants. So we're going to set up a stoichiometry dimensional analysis where we divide by the molar mass, so the molar mass is in the denominator, and you get that off the periodic table. There's a reason why those are yellow. I made my periodic table yellow. You need to do that for both of your reactants, and then that's going to equal the moles that you actually have in this process. So if I have the cards this way, this is just saying it's going to equal the moles. And that's the moles that I have of each of my reactants. So this is part of step 1 after you have the balanced equation. Next, you're going to take these mole amounts and you have to do a ratio problem to compare which one of these is going to be completely consumed and which one is going to be excess. So I'm going to take these off. You're done with that step. And what you're going to do is you're going to start your problem with your moles that you have of each of A or B, whatever they are. And then we have to do a mole ratio where we have to compare, let's say, let's just say this is A. We're going to compare A to B. That's going to give us a mole of B that we would need to consume all of this one, which we'll say is A. Then what you're going to do is do the same thing again with a little bit of a twist. So this is the moles of B. You're going to compare the moles of B to the moles of A. These numbers right here are these mole ratios off the balanced equations, and that's going to give you the moles of the other reactant that you would need to be completely consumed. So you read it as, if I have this mole amount, this is the mole amount I need to react this completely. The other choice again would be as if this is my moles of A, this is my moles of B that I would need to completely react it. Here's where you have to do the thinking. One of these numbers will be larger, one of them will be smaller. So let's just say that right here you compare. So this is my moles of A. Let's say my moles of A right here is smaller than the number over here, because this will also be A. If that's the case, you have some proof as to who is limiting or excess. Let's try the other way. You'll have both, this scenario will happen every time. What if this number is larger and this number is smaller? Remember, these are moles of B that I have and moles of B that I would need, and that would be to consume this A. So when you stop at this point, this is how it's always going to look. The only difference is these may have switched places. So this one would be smaller, this would be larger. So what you can do at this point is you can say, if this number is larger than this, that's my limiting reactant, because I would need way more moles than I actually have. So what I'm going to do then is say that would be the mole amount that I'm actually going to remove from this process. That should also mean that this should be my excess reactant. So if this number is larger than this number, then that means I have more than I need, and this is actually what I'm going to end up using. So this is my used of my excess, and this is what I actually have. So this would actually be taken off the board and not be helpful at all. These are the 3 numbers you need to calculate the excess reactant, what you used, and then products. All right, so that's step 2. That's the most complicated step. After that, the best policy is to keep your limiting reactant. So I'm going to remove these for just a second and put these down here for later. Put these actually off on the side here. I'm going to take these off. Now what you're going to do is you're going to start your problem with your limiting reactant, and let's say you want to calculate the mass of C or D. Let's just say let's do C. So what you need to do then is use a mole ratio where you compare, let's say that was A that was the limiting, but we want to convert it to C, so you just switch it out and you can write a new mole ratio. And this would be the number that goes right here, and this would be the number that goes right here. And then that's going to give us the moles of the product that we're going to get. Okay, so I'm just going to put another mole thing right here. So that's the moles of the product that we're going to get. The other thing after this is typically you want the mass of that product. So you're going to take this mole amount that you have. Let me see if I can just fit it even on here and slide these over. You're going to then take this mole amount, and to get it to mass, you have to multiply it by a molar mass of that C. And then this time you want to have the molar mass in the numerator. And when you're done with this problem, you slide these all over, you should have then this equals the mass of that product, just barely fits, the mass of that product, let's say C, that you're looking for. So you start with your limiting, you convert from A to C using your mole ratios, you then get that mole amount, and then you can convert it to mass. The last step of this kind of generic problem. So find your excess reactant, find the moles that you had. Remember, that would be a larger value than the moles that you actually needed, which was the used of the excess. You're going to need to subtract those two mole amounts, and that's going to equal the unused mole amount of B in this case, which was our excess reactant. After you get this done, there's usually two places that you're going to go after this. One is you can calculate then the mass that's unused by multiplying this by the molar mass, which is then going to equal the mass of the unused reactant B. So that's the answer here. And again, you can always slide these together and have it like that, okay? The other thing that sometimes is possible is they want to know the mass that you did use, okay? So you can either subtract it, or you can just pull this number down here, which is the moles that you actually used, and you multiply it by the molar mass, and then that'll equal the mass, in this case, let me move these off. This would be the mass that you actually used of B, because it was what you needed to react the other A away. All right, on to the practice problem. Here's a nice fill-in form that you can use for solving any of these practice problems that are limiting and excess stoichiometry. All right, so here's our practice problem. We're going to take ammonia and react it with oxygen and turn it into nitrogen monoxide and water, all in their gaseous forms. 4 to 5 to 4 to 6 are going to be the mole amounts that we use in our mole ratios. So what if we started with 2 grams of ammonia and 4 grams of oxygen? Here are the questions that we're going to answer, and we'll answer them one at a time. First is, the most important, is which one of these two masses is going to limit our reaction. After we do that, we're going to calculate the mass that's theoretically possible of the nitrogen monoxide. And last but not least, we'll calculate the excess reactant in mass, just like I showed you with those cards. Okay, so these are our goals, our 3 steps. All right, so first off, let's start with the masses. So we have 2 grams and 4 grams. So this is where we start with 2 and 4 grams of each of those reactants. You're then going to find the molar mass, and you're going to divide. I'm not going to use the little time signs. I'm just going to shove them up next to each other. So this is where, again, your teacher may just have a line. 2 divided by 17. And then this is the molar mass, and I got these off of the periodic table over here. So remember, I used this to get these molar masses. That's why I have them in yellow. And then if we stop at this point, this is going to equal, so I will try to find some equal signs here. Where are they? Here we go. This will equal the moles of that reactant. So here are my mole amounts of these 2 reactants. So that would be, after you write and balance the equation, here's step 1 done, okay? So next I'm going to do is keep just these mole amounts on the sheet here and move these off. And then we're going to do is say, okay, we have to figure out which one of these mole amounts is going to limit our reaction. So if I have 4 moles for every 5 that I need, I would get this amount of oxygen that I need. So I'm going to put my equal sign right here. Okay, so this is the amount of oxygen that I'm going to need to react away all that ammonia. All right, and next we're going to use the same, basically the same mole ratio inversed. So for every 5, we need 4. And then that's going to equal the moles of the oxygen that we're going to need to consume. And this is the amount of ammonia that we would need to get that oxygen completely reactant. And again, here's where you want to look for who's smaller and who's larger. So I'm going to grab these back, so kind of make your guess at this point. So if your prediction was that this number is larger, which it definitely is compared to this number, which is smaller, so what you'd read that as is this is the amount of ammonia that we would need to react all of this oxygen away. And we definitely have more than that number. Next, if you look, this number is smaller than this number, which is telling us that if we wanted to react all this ammonia away, this is the oxygen we would need, and we do not have that amount of oxygen. So what that shows us is that ammonia is our excess reactant, our oxygen is our limiting reactant, and the amount of ammonia we're going to use is this value right here, the 0.100. And then this value is of no use because it's not possible. So on to the next part of the problem, which is calculating the mass of the product nitrogen monoxide that we can make. The mass of the product nitrogen monoxide, I just picked that one. You're going to want to start again with your limiting moles, which was the 0.125. We're going to then convert to moles of the product, so 5 moles of oxygen for every 4 moles of nitrogen monoxide. And then that would equal 0.100 moles. And then what we need to do then is convert that back to mass, and the molar mass of nitrogen monoxide. Again, remember, I got that from the periodic table by adding up the N nitrogens per mole and the oxygen nitrogen per mole, which is 30. And then that's going to equal the mass that we're going to produce of that product theoretically, again, theoretically in lab. So there's the mass of your product. So we have one last thing to solve, which is what is going to be the excess mass and the used mass of the reactant of, in this case, ammonia. Step of the problem. So what we need to do now is say we started with this much of our excess reactant, okay? And then we only used, or we only needed this many moles. So we're going to subtract it from the 0.1. That was what we actually used to react with the oxygen. That was the limiting. This is then going to give us the moles of the excess that was unused. Okay, so this was actually the used, this was the unused. And in this problem, they want the mass that is. So what you're going to do next is you're going to multiply that by the molar mass in the numerator. Again, that number came from the periodic table, the 17. And then that's going to equal the mass. So I'm going to slide these over. That's going to equal the mass that we had that we did not need, or that was extra. So about 0.306 with sig figs was extra. The other thing you could do is you could calculate what you used, but think about it. Remember, you have 0.3 that we didn't use, 2 that we had. So you could do a little math and figure out that it's probably 1.7, because these two will have to add up to that. The other thing you could do is just pull this problem down and move this molar mass down, and you could calculate then a separate problem where you take the moles that you used, okay, this is the moles that I used, multiply it by the molar mass, and I get the mass that I actually used. So there's another way to solve this problem. All right, well, I hope that helped you. Good luck, chemist, and solve some stoichiometry problems on your own.